Okay, so we're going to continue now, and I'm going to ask that one or two of the past participants in this tournament, when I say this tournament, I mean Young Physicist Tournament, which is basically IYPT, but we started off with the German Young Physicist Tournament. I'd like to ask if we can start off actually with Frank and then ask Devin, if Devin is still online. I just want to see if Devin is still online.
I'm still here. Yeah.
Are you still there? Okay. Thank you, Devin. If Frank and Devin can just give us a little bit of insight into how they experienced IYPT, they're actually both the GYPT, and we just ask one of the Leah and Rudolf, just why you found this an important, having had a valuable experience with IYPT. Maybe we can start off with Frank, if Frank doesn't. Can maybe also just explain what you're doing at the moment, Frank?
Oh, sure. Sure. Hi, everyone. So I am Frank Smuts. I did the German Young Physicist Tournament back in 2017. So it's been 8 years. A lot has happened since. So currently I'm doing a PhD, doctorate in mathematical physics at the University of Cape Town. So that's keeping me very busy. But the reason I'm bringing this up is that I feel that the GYPT played quite a pivotal role in actually taking me on the career track of becoming a trainee physicist. Because I did one of these problems back in 2017. It was this problem on Schlieren photography. So Schlieren photography is a way that you can measure, for example, the air density above a flame, right? So you look at how the actual flame distorts the background behind it, and then based on this, you can actually infer how dense the air is that's in that air column that's flowing over it. So this is a project that I took to GYPT and then developed further for ISCOM Expo. And this is also an important thing to mention when you participate in SAYPT. The problems that you do work on here, you can also take further to other competitions like the ISCOM Expo. And I ended up taking this project quite far. I went to the Intel Science Fair in Pittsburgh, Pennsylvania. So that was through the ISCOM Expo, right? So the GYPT was kind of a fundamental experience, right? Learning how to present my work, right? And seeing what kind of the standard of physics is internationally. And that's influenced everything that's happened since. It taught me how to do experimentation. It taught me how to do analysis, or at least practice, right? I've learned so much since then, but that was a really important starting point for me. Right, that's my overview comment. Devin, do you have a comment?
Yeah, sure. So, I mean, yeah, it is one of the main things that got me into, to a large extent, into physics. I was already pretty interested. During and then after the Young Physicist Tournament, it really kind of propelled my interest to the point where I was reading a lot of maths books and physics books, so that helped me a lot in uni. The project I did was I explored Leidenfrost stars, which happened during the Leidenfrost effect, which is effectively fluids levitating off surfaces that have very high temperatures. due to rapid evaporation on the bottom of the water droplets or liquid droplets. And I didn't do anything further with that aside from take it to the German Young Physicists Tournament. From that point, I went through uni at Stellenbosch. I eventually got a master's degree in theoretical particle physics. And now I work for a forensic actuary company. So yeah, and that's, I would say that the tournament did have a big influence on me in propelling my understanding of maths and physics, and then problem solving ability in general as well because of that. Yeah.
Devin,
Hi, Don. I think there's some connection trouble. Your audio is spotty in places.
okay, all right. Let me see if I can just quickly sort it. Can you this? Frank, did you hear that?
It's working now.
Okay. Yeah. So if I can ask,
Yeah, so I think just repeat.
If I can ask Leah, each should do just a minute or two on the value that derived from the IYP.
Connor, would you like to comment on your experience at IYPT?
Sure, absolutely. So just give me 2 seconds. I'm just moving my laptop. Yeah, my experience at IYPT was pretty amazing. I'm gonna preface it by saying anybody who is looking to get into it, IYPT is very, very difficult, as you've seen. And I sort of set out to do it because I knew how much of a challenge it would be. But I think it was very eye-opening for me to sort of see the level at which these international teams operate. Because when you watch Singapore or Switzerland or Slovakia in a physics fight, it's quite a humbling experience, but it's also very eye-opening to see the levels that are out there. I also think there is so much you learn from going through a process like IYPT beyond just the physics, because obviously you learn an insane amount about physics and mathematics, but also I think the soft skills that you learn through it, the discipline, the hard work, the planning that has to go into it, that was extremely valuable to me, even more so than just the physics that I learned from the tournament. So I think it is a very good tournament to do in high school, because you learn all these incredibly valuable skills, and you really get to sharpen your problem solving ability and your ability to present your work and to defend it as well. So for me, that was extremely valuable, was all the soft skills and that development that I derived from the competition. And I would highly recommend it to anyone who's interested. It is very difficult, but in the long run, it is worth it. And you will learn a lot from the experience, 100%.
Thank you, Connor. That's fantastic. Liat?
I think Connor does say everything that I would like to say, but just to add on, you don't realize how much you change after IYPT and like before IYPT, based on like physics understanding and like the way you reason with things and like what to look out for in science and in scientific investigations and those type of in those type of aspects. So I really did enjoy IYPT in that way, that I learned a lot about it's the best way to sorry about that. It's like the best way to learn physics in a way that you could actually do. You can do it hands on, and that I really enjoyed. Also, the second point is just when you're in IYPT, you are filled with people who are more knowledgeable than you, people who've may have been at IYPT before, have like lots of, or is a master's or PhD physics like team leaders and stuff. And what you see is like in that community, like how physics is like so important to many people, and you can build bonds, and you can see like what you want to be when you're older based on just seeing people like and how they communicate in physics.
Thank you, Liat. Finally, Rudolf, I would like to ask you how, can you tell us a bit about the process that you went through in developing the work that you've presented in your presentation?
Okay. So I started off, as everyone, I think, with just going through the reference kit, which they provided. So just read through every single article and watch every single video. And after that, it like gave me quite a solid understanding of what I want to do with the problem and what there is to investigate. But one of the articles which I found most useful wasn't actually in the reference kit itself. So it's still really important to do some research on your own and not just stick to the reference kit. And there's also a few YouTube videos which I thought which were like really well made and like high quality, which did a lot of stuff that I did. And then to make the experimental setup, I didn't really see much of what I wanted to do in like anywhere on the internet really. But I just decided to do whatever's easiest, and I asked some of my friends for like ideas or tips, especially my dad, who's a mechanical engineer. And I think one of the most important things with your experimental setup is to just do the easiest thing that works. Because if you try to perfect it and like minimize error in every single way possible, then it ends up taking like way longer than it has to. So like I spent like 2 months on my second problems setup, which then in the end didn't really work at all. So yeah, and then from there I just did what I read about, and I had some help from Mr. Smuts especially, and yeah, that's about it.
Thank you, Rudolf. That's very good advice, especially the point about starting simple. With these problems, it's best to just get the phenomenon working, and then you layer complexity on top over time.
Frank, can I please ask that Dr. Douglas just quickly say a few things about what he's observed over the past few years, and then we can move into the discussion of the 8 problems thereafter. Dr. Douglas?
Thanks very much. So to me, the main thing is to see the participants have this experience that they wouldn't have had any other way. It is physics that is at a level beyond school. I think we've mentioned this a few times. And we don't always have an opportunity as teachers on the one side and as students on the other side to engage with things that are of such a high level. So having the opportunity to do so, and in a structured way, I think is very important. And based on that, the growth that you see in the participants from when they start to when they present at IYPT is just phenomenal. You go overseas, you go to this highly pressurized environment with 35 teams of 5. Yeah, you do the math on that one. Of high-performing, smart, intelligent, witty, clever people, your peers. You are among the best of the best in the world in this field, and the amount of growth that takes place there by interacting with them is unbelievable. I've seen them work hard and I've seen them play hard. And I think that's part of the IYPT. Something that we tend to overlook in the end is this experience that that we have. It's not just about the physics. It's about meeting new people, about engaging with students at the highest level, engaging with their cultures. You know, we had at the IYPT last year or this year, we had participants from Iran, we had participants from the Ukraine, we had participants from China, we had participants from Taiwan, we had participants from the USA, among other countries. And so, you know, whatever's happening in the world, you sort of get a microcosm of that at the IYPT. But there, all the political differences between the countries don't matter. There you are just a bunch of young people who are united in your pursuit of an understanding of the physics and getting to know each other better and learning more about each other. And I think that might be one of the unsung takeaways, is that you're building a foundation there for dealing with like-minded people, and you know, maybe that is a bridge then to the future, and making a better world in the end by putting smart, clever people like that together all at once. There's also a beautiful cultural aspect to this. You get to go to countries where the ways are not the same as where you are from. You get to experience things such as public transport, for example, that you won't be able to experience here. There are lots of cultural exchanges happening. We went to Sweden, so we would visit a Viking village and swam in the Baltic Sea, and all kinds of other experiences that you wouldn't otherwise have had beyond that of the physics. So I think in terms of personal growth, it is also a very, very useful and interesting and important experience.
Thank you, Dr. Douglas. Yeah, and we, you know, we all are very passionate about this, and we're well aware of the fact that unfortunately international travel makes it very expensive to participate in the IYPT in a face-to-face tournament. But we, you know, all Dr. Douglas and Frank Smuts and myself have all felt that we want to make the wonders of IYPT, all the, you know, the benefits we can gain, that can be gained from IYPT, to be made available and made more accessible in South Africa. And that's why we have created this SAYPT, which is free and is online. And my encouragement is that as you go through this process, it's not just a competition, it is a program. And I want to emphasize this, is that you must please engage with us when you come, you know, you reach a a challenge or a dead end, that, you know, we are also there to give you guidance and instruction. This is not just about a competition. This is about helping young people to facilitate growth in their own physics journey. So while you may not be face to face with this community, we can be online, and we can help and guide and share with you. And this community continues to grow. So yeah, please don't just see this as that, well, you're on your own and you're going to be only doing a competition. This really is a young physicist program. So now I want to hand over to Frank, and Frank is going to deal with the 8 problems that have been selected from the 17 IYPT problems for SAYPT. Thanks, Frank.
Thank you, Don. Yes, so let's talk about the South African Young Physicist Tournament and the 8 problems of which you can choose, right? So there's something for everyone. Let me share. I think just give a thumbs up if you can see my screen. Okay. All right, so let's look at the problem set. Right, so in the IYPT, there are 17 problems, but we've narrowed down to a subset of 8 problems, right? And these are what we will assess in the South African Young Physicist Tournament. What I want to do here is go through each problem statement, kind of just do basics of how to analyze a problem statement, and give you some pointers on what independent variables you can look at and what physics concepts you should look up. So our first problem is invent yourself. So the problem statement says that a self-starting siphon can be made using a piece of rigid tubing bent into a specific shape. When the siphon is partially immersed in water, it begins siphoning water without the need for initial suction. Investigate how the relevant parameters, such as the geometry, affect the siphoning process. Okay, so let's break it down. In the first place, in bold, that's what do you need to build? Well, you need to build what's in the video on the left-hand panel, right? A piece of rigid tubing bent into a specific shape. Then, what do we need to observe in this setup, right? When the siphon is immersed in water, it should siphon without the need for initial suction, right? So this is different to a normal water pump where you need to put some energy in to pump water out. This siphon operates by itself. Then, what do we need to investigate? Well, we need to investigate how the geometry affects the siphoning process, meaning the shape of your siphon. So, let's go over possible independent variables, okay? Possible things that could affect your siphoning are the tube diameter, the lengths of the tube sections, and even the angles of the tube sections. So if you look at the siphon on the left-hand side, one of the tube sections is at an angle, whereas the other three are parallel, right? And then the dependent variable would be the water drainage rate, or how quickly the siphon removes water from your water source, okay? And you can also look at how much water it siphons. Then some concepts you can look at are just siphons in general, but if you want to physically explain what is going on with the phenomenon, you should probably look at what's called the Bernoulli's principle, which talks about pressure differences in tube systems like this, right? So that's the first problem. And now we've kind of looked at how to break down the problem statement. Let's do another example with electrical damping. But before that, I would like to comment here that your approach is very much the scientific method that you've been taught in class, right? So the point is you have to make observations, you need to ask questions, right? You need to see, okay, what are the relevant independent variables for your problem? Here we've already given you the research topic, but the point is that you need to form hypotheses and test those hypotheses, and reject those hypotheses and change those hypotheses, right? So it's an iterative process, like Rudolph said. And then in the end, you communicate your results, as we've shown in the physics slide. So let's look at the second problem, electrical damping. So this is more for people who are interested in circuits and magnets. So a magnet suspended by a spring will display simple harmonic motion when displaced. If the magnet oscillates within a coil connected to a resistor, its motion will be damped. Investigate the factors that affect the damping. So again, let's break this down. What do we need to build? Well, we need to build a magnet suspended by a spring. And with this setup, we will observe simple harmonic motion. And simple harmonic motion is just what you see on the left, right? You pull the spring, you release the magnet, and then it oscillates up and down. And it will keep doing this for a very long time. But if you put the magnet inside a coil connected to a resistor, its motion will become damped, meaning that the motion will peter out and it will just slow down to a steady state. So crucially, you have to investigate the factors that affect the damping. All right. So independent variables are the current in your circuit, the resistance of your resistor, the inductance, the magnetic field strength, so how strong your magnet is, and even things like the spring stiffness. Then the dependent variable is the motion of the magnet, but more specifically, the damping rate. So in Rudolph's presentation, you would have seen an example of how to measure the rate of damping. of an oscillator, right? He looked at a pendulum, but the ideas carry over to a magnet on a spring as well. Then some concepts to look at are your circuit types. So in this case, it's an LR circuit. I put an LC, but it's an LR circuit, a inductor resistor circuit. Look at electromagnetic induction. That's probably what plays a role in the damping of your magnet. And then look in particular at magnetic damping. Right, so we've looked at these two problems in detail. I'm going to move more quickly through the remaining 6. Right, then the third problem is on oil flow. So here, a thin layer of cooking oil on a flat metal surface flows outwards when heated. Investigate the phenomenon and its dependence on relevant parameters. Right, so if you look at the left, some important parameters are the oil type, the oil volume, so how much you put into your hot surface type, right? So you can look at different pans that you can heat up on a stove, for example. It can be non-stick, it can be steel. They specify that it should be a metal surface. And also look at the heating method, right? So, for example, preheating the pan and putting the oil in versus heating the oil from cold. Then the dependent variables could be the output flow rate and the final distribution of the oil on your hot surface. Right? And with fluids, there is a lot to know. Lots of things to investigate. Density, viscosity, surface tension, convection, those are fundamentals. And if you want to go really far, study the thin film equation and the Marangoni effect. Right? Fourth problem is the autumn coin. Right, so this is a mechanics problem as opposed, well, okay, it's actually a very difficult problem if you think about it mathematically, but here there are mechanics and fluids involved. So the motion of a coin falling to the bottom of a tank filled with liquid can be remarkably similar to the fluttering and tumbling of a falling autumn leaf. Right, so if you look at the video on the left, we clearly see this sideways fluttering motion of the coin when it's thrown in. And it is your job to investigate how the motion of this coin depends on relevant parameters. So what are these parameters? What are these independent variables? Well, the coin size, the coin shape, those can matter. And the liquid type also matters, right? So you can look at water, but they specify a liquid. So you can throw a coin into anything, right? It doesn't have to be water. It can be honey, if you want to try that. And you should also even just look at the motion of a coin in the air and compare to what it behaves like in water, right? Then your dependent variables are the coin's position and rotation over time. But for this, I recommend that you actually try to qualitatively describe the motion, right? So you can, for example, look at the timing in between the steps of the fluttering motion, right? Where it's moving from side to side. And that can give you perhaps more information than just tracking the motion. All right, so again, lots of concepts here. You have to learn about momentum. This you do in high school. Angular momentum, this you do not do in high school unless you're doing a senior level course. There's moment of inertia, hydrodynamic drag, so drag due to water, and also more specialized topics such as the angle of attack and fluid numbers. Problem 5, I hope you can hear this. This is an experiment that probably most of you have already done at some point in time. So when a ruler is clamped at one end and struck, it oscillates and emits a characteristic sound. Right? If you can hear the audio, the pitch is higher when there's a shorter extension of the ruler over the edge. And then if it's longer, then you hear a lower pitch. Okay, so you have to investigate how the sound depends on relevant parameters. Okay, and those parameters could be the ruler length, the ruler material, right? Let me maybe just briefly pause this. Right, so the ruler length, the ruler material, the choice of clamping, right? And also the striking motion. Then your dependent variables are frequencies and amplitude, or colloquially, pitch and loudness, right? But kind of a misconception with when you're measuring the pitch of an object is that no object has just one pitch, okay? Right, so if you actually measure the audio, if you record the audio of some object, right, of your ruler, then you will see a signal that's been generated, right? And if you want to measure the pitch, you do what's called a Fourier transform. And that's what you see on the right-hand side. And you'll see there's a bunch of peaks there. And each peak corresponds to what one would normally think of as pitch. But in reality, pitch is not quite like in music where you say, okay, you like you play a middle C, then that's the pitch, right? If you actually study the sound in detail, the timbre, right, the full sound of an object is composed of multiple pitches that are composed on top of each other, right? So these are the frequencies, right? The frequency spectrum. So that is something to investigate with this problem, right? So look at vibrations and waves, elasticity, Fourier transforms, and the Young's modulus. That's problem 5. Then problem 6 is a very different kind of problem. It's a crystallization problem. So if you look at the left-hand side, we have a little drop of salt solution on a hot plate, in particular a non-stick plate. And you see that it forms this very interesting crystal shape made of a blob and several legs that kind of push the structure up. So let's reread the problem statement. Observe the evaporation of a drop of table salt solution on a warm hydrophobic surface. After the water evaporates, a variety of characteristic crystal shapes remain. Research and explain this phenomenon. Now, this is actually outside of my field of expertise. So here I am very much guessing the independent variables, but you should look at the salt concentration, the salt type. For example, how fine the salt is might make some impact on what the structure looks like. But also look at the volume of the solution, right? So on the left-hand side, we have a little drop of salt solution, but try to vary the volume and see if that affects the structure that you see. And also look at the temperature of the hot plate. That will affect the crystallization. So then the dependent variables, this is a bit atypical because you're looking at a shape. You're not measuring something specific, you're actually looking at these crystal critters. So you need to come up with a way to talk about them. Then some concepts to look at here are crystallization, hydrophobic surfaces, and evaporation. That's problem 6. Then the 7th problem is a very cool problem. It's the magnetic Newton's cradle. So for those of you who do not know what a Newton's cradle is, that's what you see on the right-hand side of the video. You will have a couple of metal spheres that you string up like a pendulum and you put them in series, right? You hang them up. And then when you take one of the spheres, lift it up and release it, then it will hit the other 4. But the point is that the kinetic energy gets transferred all the way through to the last sphere. And then it's only the last sphere that actually really moves. And then it, pops out, hits back, energy passes through all of the spheres again, and then it produces this cycle of motion where only the 2 outside bobs are doing most of the motion. Then on the left-hand side of the video, that's a magnetic Newton's cradle. So it's the same idea, but instead of having actual contact between the individual bobs in your chain, there's a magnetic force interacting between them. So the problem statement is that repulsing, non-touching magnets are used instead of colliding balls to make a new type of Newton's cradle. So the cradle that you see on the left-hand side, the far left-hand side. The new cradle can act in a similar way to a regular cradle, but can also exhibit other interesting behavior, right? So you see there with the magnetic cradle, it's not just, flying out and coming back in. There's this very interesting interplay between the 2 magnets. So explain and study the movement of this magnetic cradle. right? So independent variables are the number of magnets, right? So start from 2, then work up from there. The strength of the magnets, the size and volume of the magnets, and even the string lengths may impact your results. Then dependent variables are the magnet motion. Again, your goal here would be to try and characterize what type of motion the magnets make. And then also look at the rate of energy loss. I think it would also be interesting here because the energy losses, right, the dissipation in the normal Newton's cradle versus the magnetic Newton's cradle may be quite different. And then finally, right, concepts to look at are pendulum, Newton's cradles, neodymium magnets, and then on the theory side, magnetic dipoles, magnetic fields and forces, and eddy currents. Right. Final problem is a subtle problem, the twisted spaghetti problem. So let's look at the video on the left-hand side. If you take a bundle of spaghetti and you just snap it, then it forms a bunch of little particulates, little fractures, right? So when you break a piece of spaghetti, it doesn't just break into 2, it actually forms a bunch of fragments, right? And if you just take a bundle and break it, there are a lot of fragments. But if you twist the bundle and then snap it, you'll see that it takes more force to actually break it. You need to apply more transverse stress to break it. And there are a lot fewer of these fractures and split pieces that fly off. So for the problem statement, when a bundle of spaghetti is twisted, it might withstand higher transverse or side forces than a straight untwisted bundle. Investigate the response of a twisted bundle to transverse stress and identify the optimal twist that maximizes tolerance to transverse stress. Okay, so independent variables. The most important one is clearly the twist angle, because that's stated in the problem directly. But you should also look at the spaghetti count, the spaghetti length, and maybe even the type of spaghetti. Then your dependent variables are likely the maximum stress prior to fracture, so the amount of energy that you need to put in before your system buckles and breaks. And finally, you have to look at the level of fragmentation. So try to talk about all these extra pieces that are created when you break the bundle. All right, so here again, there are some mechanics concepts to investigate, in particular stress. By this, I mean physical stresses, bulk stress, shear stress, transverse stress. Then also look at torsion, torsional rigidity, fragmentation, elasticity. All right, that is problem 8. And by now, I've covered everything, right? So those are the 8 problems. With an outline of what sorts of parameters to look at and what sort of concepts to look at. And I leave you with a bibliography, in particular the IYPT reference kit, I think is a very good source. It is a compendium of references on the various problems that you can refer to as kind of a starting point to start understanding the problems better.
Thank you, Frank. Appreciate all the effort and hard work that went into you preparing that. And at this stage, I just want to deviate a bit from the program. Are there any questions directly on the problems from the new participants? Is there anyone that would like to ask a question? You're welcome to actually switch on your mic and ask the question verbally if you would like, if there are any. All right. If there aren't, then I'm going to move on, and I would like to just share.
Sorry, so there is a question here.
Oh, is there? Okay.
Yeah, Xiaoyan wants to just ask us a question.
Okay. Sorry about that. I didn't pick that up.
So if we chose like a question already in the form, can we change it or are we stuck with it?
You can definitely change it after your registration. Yeah, after the early registration. I think it's good to have a look at a couple of the different problems and see what you really like and then decide on one. Right. So I think, yeah, it's better not to just attach yourself to one project just because you did it because you chose it in the initial registration. Your final submission is in February, I think. So you actually have a lot of time to work on these problems and decide.
Yeah, thank you very much for that. That was a very valid question, and I agree 100% with what Frank says. Sometimes you start on a problem and then it goes, okay, this is not really working, or you learn a little bit more about another problem and then you want to do that. You're welcome to. Yeah, so you choose something that interests you. I think that is the first thing. Secondly, choose a problem that is accessible to you, that you can get the phenomenon working. That's always advice that I give, is that once you've chosen your problem, try and get the phenomenon to work, even in its simplest form, get it to work. That's the first thing. And then once you've done that, then you can start fiddling with the different parameters and that you may want to investigate that have impact on the particular phenomenon. Are there any other questions? I have posted the link to Frank's presentation in the chat block, and I've also posted it on our SAYPT and IYPT site as well. And I will also be posting the recording of this. I will break it up into the main parts of this presentation or this workshop, so it's easier to access. If there aren't any other questions, then I would like to just briefly, because we don't want to keep you too long, I just want to briefly go through the timeline, if I may, and I just want to find it here. Let's just go here. If you can just bear with me. So let's see. All right, here it is. Okay. All right, if someone can just give me the hands up that they can, thumb up that they're seeing it. Can you all see it? There we go. Thank you very much. All right, so very, very, very quickly, we are now on the 4th of October, 2025. We've had our first online introductory SAYPT workshop. So on the 28th of February next year is the final registration, if you haven't registered already, and that's round one, where a 10-minute video submission needs to be made. Now, as I've said before, this is not just a competition, this is a program. Our motive is to inspire a new generation of young physicists. So you are welcome to email us. We will, if we can't help you directly because that particular problem falls outside of our expertise, we will look to find someone who can. We have got a network of very smart people who are studying postgraduate physics, but they also know other people in other fields. So the first submission is a 10-minute video presenting your experimental investigation, your qualitative model of your chosen problem. We took a lot of time today to show you the IYPT standard. Now, that is obviously where you would like to aim, but as I said before, if we don't want the mathematics to be the handbrake on this, we would like young people to engage with the physics without being prevented by the mathematics. If you do get a mathematical model going, that is great. You do need to be able to explain the phenomenon, even if it is only in a qualitative way. But we've shown you what the standard is and what is possible. Then on the 9th of March, successful participants through to round 2 are informed via email by the chief juror. Now, quite a few of the people that are presently online are going to be part of the jurors. We have also got some international jurors who we have come to know through our IYPT journey. We've got someone from Germany, we've got someone from Slovenia, probably going to get someone that I know from Greece. And there are also other previous GYPT, HYPT, and IYPT participants from South Africa who are not present today, who have offered their services. But the chief juror, who will more than likely be Mr. Frank Smuts, will inform successful participants. I myself will also help him. Then on the 16th of March, round 2, there will be an online interview. So shortlisted candidates will be interviewed by a panel of physics educators. And we will then dig deeper into your understanding of the problem, what you've done. So your video presentation must obviously cover, like you saw with Rudolph, cover the basic problem, your understanding of it, what parameters you actually decided that were important, how you set up your experiment. You saw he spent a lot of time on his experimental setup. Obviously with SAYPT, that is really very, very important. Your qualitative model at the very least, your data processing, and then we will then ask you more questions, a bit like the panel of jurors in IYPT. That would be an online interview. It'd basically be you, if you get through to the second round, with maybe 2 or 3 jurors. Then on the 30th of March, the finalists will be informed via email by the chief juror, and then starts the training for the finals. And we'll run another workshop in more detail about report and opposition. You got very good advice from Connor and from Leah today. They will probably play a role in that as well. And then the finals will take place around the 18th of April. It is subject to change. We know that next year maybe there's things that happen, and then we might need to move it. But our goal is to have it around the 18th of April. So, are there any questions at this stage on that? If there aren't, then I am going to move on and I'm going to conclude. I want to say thank you to everyone that has taken the time to be here, and I hope my Wi-Fi link is going to hold up with my video on, with my camera on. But we want to thank you for participating today. We want to thank Frank for all the hard work that he put into preparing the presentations. We want to thank those of you who are new participants that you took out the time on a Saturday morning. We know that a lot of the schools are now on holiday. We know that some schools are maybe still playing sport, the 3-term schools. We want to thank you for coming. And as I've said it again, and I'll say it again, this is not just a competition. This is a physics program. I want to thank the past participants for being here. I want to thank Connor and Rudolph and Liat for taking their fresh experience and sharing it with us. And at the end of the day, our motive here is to inspire and to facilitate the growth of a new generation of young physicists in South Africa. It's a program, not just a competition. Please feel free to contact us. You have my email address, and I will keep on putting information up on the website as we go along, but please feel free to contact us. And I know that, for instance, Radial, we are actually going to do a presentation for another presentation, a shortened one. Mr. Smuts and I are going to do that in a few weeks' time. So enjoy your holiday, enjoy the rest of the Saturday, and thank you very much for participating. Goodbye.